Hello everyone. Let's take a look at our next problem. You were given a triangle with a fixed perimeter, but you want to maximize the area. What shape will it be? Prove it. My first thought is it's probably going to be an equilateral triangle. I mean, how do I know it's going to be an equilateral triangle? Without instantly writing anything down. The perimeter is fixed, but we want to maximize the area. Now, another way I'm thinking about this, if I want to prove it, an easier way to think about this to actually prove it is if I want to fix the area and minimize the perimeter. Those two problems are equivalent. How do I prove it? Again, my conjecture is that it's an equilateral triangle. I'll retire from mathematics if that's not the answer. But how do we actually prove it? Okay, here's what I'm going to do. Everything in my mind is saying this will be easier if I do this alternative way of trying to solve the problem, which is to fix the area and minimize the perimeter. And one reason why I think this might be a little bit easier is if I imagine a triangle like this, where the base is fixed and the height is fixed, this fixes the area of the triangle. And now imagine I can grab this point and drag this point to the left and right as far as I want. If I drag this point over to here, then the triangle that I'm actually working with is this one. How will this actually, at the end of this, the point that minimizes the perimeter for all of the triangles that I can get by moving this point up here, let's assume that I can prove that the one that minimizes the perimeter is the one where the location of this point is at the midpoint of the base. Okay, so it would be here. Then I would still need to work with the fact that the length of these two sides might be different than this bottom side. I'm feeling like if I take a brute force approach to this with labeling coordinates and doing some kind of constrained minimization, it's going to be an absolute mess. Maybe not. Maybe not. I don't know. I'm kind of inclined to do calculations more than thinking about things other ways. So here's what I'm going to do. Okay, we're going to say that one point of our triangle is at the origin. I suppose I should have my axes go like this. And the other 2 points we're going to give coordinates, arbitrary coordinates x and y. This is probably going to be a disaster, but I suppose technically it should all work out. And so, I've got P1 somewhere, I've got P2 somewhere. Things could be In other quadrants, things could be all over the place. I don't know exactly where all these points are going to lie. They're arbitrary, right? So the perimeter, I guess maybe I shouldn't have used P for these things, but the perimeter, which I'll call D, is going to be the length of the three sides of this thing. So the length of P1 is x1 squared plus y1 squared under square root. P2, x2 squared plus y2 squared under square root plus x1 minus x2 squared plus y1 minus y2 squared under square root. Okay, so that's the perimeter, which, according to the question, is a fixed number. It's kind of messy. And the area of my triangle, if I remember correctly, I'm given the vectors or the points, however you want to think about them, P1 and P2. I think the area of the triangle is a half times the magnitude of the cross product. I have to think of, you have to think of P1 and P2 as existing in 3 dimensions here, but just add a third coordinate of 0. Is this going to help? I mean, I have 4 degrees of freedom. I have 4 variables, x1, x2, y1, and y2. I have a single constraint. Which will introduce a Lagrange multiplier and optimization. I'm maximizing the area, and of course, if I rotate this in any way, I'll still get an acceptable answer. I'm not going to be able to uniquely solve for the four values, is what I'm saying. This is too messy for me to want to continue with, at least with this approach. What might be another nice way to think of this? At the end, we don't actually have to solve. We're not trying to solve for x1, x2, y1, and y2. What we're trying to show that these 3 numbers are equal. So if I write down the optimization that I'm trying to do here, maximize the area with this constrained, this should give me a system of equations that need to be satisfied by my variables, and maybe I can manipulate that system of equations to show that these 3 numbers under the square root signs have to be the same. Yeah, I don't know if I like it, but I'm going to try. The first thing we need to do is write this area in terms of my variables. I don't really like all the square root signs in the formula for the perimeter, but I don't know if there's a way to get around that. So what I'm trying to do here is I'm trying to maximize A subject to, let me just write this out, maximize x1, y2 minus x2, y1, absolute value. I don't need the factor of a half here, because if I'm maximizing the area, that's the same as maximizing twice the area. Subject to x1 squared plus y1 squared root plus x2 squared plus y2 squared root plus x1 minus x2 squared plus y1 minus y2 squared square root is equal to d. So for the same reason that maximizing the area of something is the same as maximizing twice the area, which is why I can get rid of that factor of a half, it's also the same as maximizing the square of the area. So I'm going to define a function just simply the thing that's I'm going to be able to take derivatives of here, and I'm introducing a Lagrange multiplier because I'm thinking of this as being a constrained optimization. Don't quite have enough space for all this. Let's make it a little smaller. Okay. Now it's not going to be easy, but I'm going to be taking derivatives of this thing with respect to my 4 variables. Let's allow this to depend on lambda as well. This is going to be real messy. Don't know if it's going to be the best way to work things out, but yeah, we'll see. All right, there's my derivative with respect to, partial derivative with respect to x1. Oh, I'm missing, there should be a y2 here. And I guess I need a negative sign there. Okay, the derivative with respect to x2. And the derivatives with respect to y1 and y2. So I have 5 variables, the x's and the y's, and lambda. All 4 of these expressions should be equal to 0. And I also have my constraint on the total perimeter. Is there a way that I can, so I have, And what I want to show is that these quantities here are equal. I don't know if this is going to be easy at all. I don't see how to do this. You know what? I don't know. I think part of my sort of natural intuition to start might be a better way of doing this. Let's sort of narrow it down. Yeah, I'm not proceeding with that. I'm going to go back to this diagram that I had earlier on. And while I was writing out those equations, I had another idea. So I'm still going to think about it in terms of trying to minimize perimeter for a fixed value of the area. But for what I'm going to do is, again, sort of just assume that these 2 points here are fixed, and that what I'm doing is I'm moving this point left and right. And what I'm going to do is show that the point which minimizes the perimeter is at the halfway point of the base. But then the argument I'm going to use is I selected the base of the triangle to be, I selected it arbitrarily. So the same thing would be true if I use this as the base, then moving this point parallel to the base, the point which maximizes, or sorry, the point which minimizes the perimeter is the one that's going to be at the halfway point of the base. And so what I'll have is that all three points, if I want to fix the area and minimize the perimeter, each point has to be located on the perpendicular bisector of the opposing side, because if that were not true, then I could shift the point parallel to the opposite side and have something with a smaller perimeter. I think that'll be a better way to do it. And then if I have a triangle where all 3 points are located on the perpendicular bisector of the opposite side, that's an equilateral triangle, right? I'm not making that up. There aren't triangles. There aren't other triangles, right? Okay, so let's do it that way. It's a lower dimensional problem, right? I only have 1 degree of freedom in all of this, and so it should be a lot easier just to show that I should end up at the midpoint. Okay. So what do I need to do here? I'm going to label this as D1 and D2. Where should my frame of reference be? I'm going to say that this lies at, so the distance from the point on the left to here, I'll call that X. And the entire length of the base here, I'll call capital L. So if I take this point, if I move this to the left or right, parallel to the base, all of those triangles that I have, and of course I'm resketching, I would have to resketch the sides. Those all have the same area because the base is fixed and the height is fixed. So what I need to do is I need to write down D1 and D2 in terms of X and minimize their sum. Okay. I suppose I need a height of everything here as well, right? Yeah. So d1 squared is equal to h squared plus L squared. And d2 squared is equal to L minus x squared. Oh, this should be an x. L minus x squared plus h squared. Okay. So d1 plus d2 is some expression with some roots in it. Okay, I'll just call this a function of x. And I want to minimize this perimeter. So I'm going to take a derivative of f with respect to x. Okay, and this should be equal to 0 when x is a minimizing value of my function. Okay, so what do I have here? X squared plus h squared to the negative 1 over 2 times x minus L minus x squared plus h squared to the negative 1 over 2 times L minus x is equal to 0. So x equal L over 2 certainly satisfies this. If x is equal to L over 2, then that quantity is equal to that quantity, and that quantity is equal to that quantity. And I guess if we want to claim that this is the only solution, we would have to look at what this function looks like as a function of x. Or we could do some second derivative tests and so on. I mean, I'm fairly confident that this is the only solution to this. So what is this saying? This is saying that, you know, if I'm moving this point along this direction here, then the point which minimizes the total perimeter of the triangle is the one that's at, it's the one that's at the halfway point of the base. But this has to be true for all three sides. If I, like I said earlier, if instead I declare this to be the base of the triangle and I'm allowed to move this point along this axis, then the same thing has to be true. It's just reorienting your perspective here. And so what this is saying is all 3 points must lie on the perpendicular bisector of the opposite side, and that's got to be an equilateral triangle. Yeah, I mean, my intuition often is always to just sort of brute force things. It's nicer to do things in a more elegant way, but hey, you play to your strengths sometimes. Thanks for watching.